Welcome to this lecture series in linear algebra. In this lecture, we'll look at functoriality and naturality of the double dual, whatever that means. We will define everything. And let us recall what we need. So we will need to know about dual spaces. So for any vector space V, we can construct the corresponding dual space, which is by definition the set of all the linear maps from the vector space V to the base field. So this has a natural vector space structure, and this has the same dimension as that of V. We defined the notion of the transpose of a linear map, which is essentially just the corresponding notion for linear maps as the dual is for vector spaces. What I mean by that is the following. So let me recall the definition of the transpose. If we have a linear map between two vector spaces, the transpose of this linear map is a map from W star to V star, which takes an element of W star and outputs an element of V star in this fashion. And as I said in my video, a more appropriate name for the transpose would be the dual of the linear map. All right, and we of course need to know about this natural isomorphism between the vector space and its double dual. We are not explaining what is meant by the word natural here, but hopefully in the course of this video, the reason for this phraseology or terminology will be more clear. So what does this map do? It picks some vector V and outputs, by notation it outputs this guy. But what is this map? This map picks a linear functional on V and just evaluates it on the vector little v. So this is an isomorphism, and with these things, let us proceed. So what is functoriality? So here we have some commutative diagram of, in the world of vector spaces. So these are vector spaces and these are linear maps. So think of them as cities. The vector spaces, think of them as cities, and the arrows you can think of as traffic or the roads going from or connecting the cities. So suppose we have a map S and a map T, and here is the composite of them. So this diagram of course commutes. So what we can do is we can for the moment forget about this one and create this diagram. So here we take the duals of all the vector spaces that are present in this diagram, and we dualize the linear maps also. That is, we take their transposes. Question is, what is this map? What is the composite of this and that? And it is as good as things can be. This happens to be the transpose of the composite, right? So the transpose of the composite is the composite of the transposes. And this is what we have written here. We will show this. But what it is saying is the following, that given any commutative diagram in the world of vector spaces, you can create another commutative diagram just by reversing all the arrows, decorating all the linear maps present by this little t so that they become transposes, and decorating each vector space by a little star on top so that they become the duals of themselves. So every diagram in the world of vector spaces has a corresponding quote-unquote inverted version of it. All right, so let me just finish this diagram and then we will continue with the proof. So this arrow is, of course, it is the same as the composite of T transpose and S transpose, but what we will show is that this is actually the transpose of the composite. Okay, so showing this is just a matter of unraveling the definitions, but let us try to show this by means of diagrams. So if we, let G be some arbitrary element of W star, what we want to do is show the following. We want to show that, let me write it in the reverse way. So we want to show that this thing is equal to that thing. Right? So let's start. So we have this functional G on the space W. All right, and here we have our vector space V, This map is T. And what is the composite? This composite is, by definition of transpose, same as T transpose of G. Right? This is how we saw, this is how in fact we defined the transpose. Okay. Perhaps I missed explaining that in the beginning of the video. Yeah, no, this is how it is defined. All right. So yeah, so this is the transpose of T applied to G. And now we further have this thing with us. This is S, and here is a vector space U. So what are we doing? We are composing a linear functional on V with a linear map mapping into V. So this guy is the transpose of S applied to this linear functional. So this guy, this arrow is same as the transpose of S applied to this linear functional, which is of course S transpose composed with T transpose applied on G. All right, that's one way. The other way is we have a linear functional on W. Call it G again. You can't call it G again, it is G. And then we have the composite of S and T. This is S, this is T, this is U. And this composite is T composed with S. And now what about this arrow? This is the composite of G and this linear map, and hence it is equal to the transpose of this linear map applied to G. So this arrow is this transpose applied to G. But this arrow is same as that arrow, right? We are just kind of doing things in a somewhat different order is all. This arrow and that arrow are exactly the same. This diagram and this diagram are exactly the same. So therefore this must be equal to that. And this is what we wanted to show. And therefore this holds. So this establishes what is called the functoriality of the dualizing operation. Functoriality is just referring to the fact that commutative diagrams become commutative diagrams under a certain operation, which is in this case dualizing. Okay. Now we'll talk about naturality. So fix or start with a linear map from a vector space V to W. We have the transpose of the linear map, which takes the dual of W to the dual of V. And then we can further take the transpose of it to get a map from the double dual to the double dual. So first we had a map from V to W, then from W star to V star. So here kind of the arrows got reversed, but then they again got reversed, and we then have a map from V double star to W double star. But recall there is a natural isomorphism between V and V double star, which we denote by this guy. So just to beat it down, it is the map which takes little v to, by notation, this guy. But what is this map? This map picks the functional on V and outputs the evaluation of F on V. Right? Similarly, we have this phi W, which you can write down if you want. Just the exact same thing. So we have the natural isomorphism and we have a linear map sitting on top. So since these are isomorphisms, we will obtain a linear map here which makes this diagram commute. In a manner of speaking, it is kind of pushing this linear map down to this level, if you will. And the interesting thing is that this is actually the same as the double transpose of T, or said better, it is the double dual of T. So this double dual operation picks a linear map and produces another linear map, but they are connected via natural isomorphisms. So in some sense, there is no difference between this linear map and that linear map, as long as you remember the recipe by which you are allowed to change the names of things and the traffic. So this recipe is how you change the names, and then it kind of allows you to see that this and that are exactly the same things. Okay, and the proof is, again, just a matter of unraveling the definitions. So first note that proving, so before before we continue, yeah, what is this guy? I mean, you go via this inverse arrow. So phi v inverse, then you apply t, then you apply that. So this map by definition of the diagram is this, right? But the theorem or the fact that we are proving is that this thing is actually that thing. So this arrow which makes this diagram commute is necessarily this guy. So that is what we are going to prove. And note that this is equivalent to proving this composite is same as this composite. Why? Because look at the left hand side. If you compose the left hand side on the right by this guy, what you will obtain is this thing. And if you compose the right hand side by the same thing, what you will obtain is this. And therefore, proving this and proving that are the same because this thing is an invertible linear map or a linear isomorphism in other words. Okay, so this is what we want to do. And to show this, what we really want to do is the following. We want to show that this behaves the same as that on every element of capital V. Because what is this? This is a map from capital V to W double star and same as this. And we want to show that these two maps are same. So we want to show that they behave the same on every element of this vector space V. So fix some little v. And now our goal is to show that maybe I'll take some space. That this happens. If you take the value at v of the left side, this is same as the value at v of the right side. Okay. But that is same as saying that is phi w of tv is equal to t double transpose of this thing. Right? But just a change of notation. This is same as that. And the right side is this thing. Okay. And now this thing is an element of W double star. And of course, this thing also is an element of W double star. Maybe you want to look here to understand that. And we want to show these two things are the same, meaning these two maps from W star to S. An element of W double star is a map from W star to F. So we want to show that these two maps are the same. And these two maps will be the same if they behave the same on every entry of W star. So fix an element of W star. And now the reduced goal is to show that this, when we feed G to it, is same as that thing. Okay. So I need to make some space. But this left hand side is equal to by definition of this entity is equal to that. And the right hand side is again a matter of unraveling definitions. This is the right hand side, but what is this? Yeah, this is a little bit trippy. So let's try to understand. What are we doing? We have T transpose. So think of T transpose as some linear map. We have a linear map whose transpose we are taking, applying it to an element of W double star, and then evaluating at G. So if you just unravel the definition of the transpose, you will get this is equal to this entity, and again, using the definition of this person, we get this is equal to T transpose of G evaluated on V. But now again use the definition of transpose. This is G of T transpose of V. Sorry, G of T of V. And that's it. Okay. So in this step, think of T transpose as some linear map. Call it whatever you want. Call it S. So this is now S. So S transpose of a functional on W star evaluated on a vector in W star is the functional evaluated on S of the vector. If that makes sense, but you can go to the definition and you will agree. And then again use the definition of the transpose you get here, definition of this guy you get here, and then use the definition of the transpose to get there. So all of this is just an exercise in definitions, which I encourage you to do for yourself rather than look at what I am doing. But anyway, so this is equal to that. So therefore, this is equal to that. And that was our reduced goal, and that's it. So this shows this equality. But the larger point here is the philosophy that this whole diagram is trying to convey. There is some truth in the original world. You double dualize it, you preserve the same truth as long as you know the password. So these are kind of your passwords to move between the two different looking worlds, but they have exactly the same information. Okay, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.